Hey everybody, this is Mr. Piercy, and what we're going to be doing in this video is taking a more in-depth look at Taylor and Maclaurin series. Now this is not to be confused with what we've done with Taylor and Maclaurin series or polynomials already in our calculus studies. What we're going to be looking at today is not going to be how we can show a Taylor polynomial can be used as an approximation for a more complicated series or expression. Instead, what we're going to be looking at here is showing the relationship between a converging power series and a Taylor polynomial, as well as illustrating how we can do kind of piece by piece or part by part differentiation or integration of a Taylor polynomial or Taylor series. So that's primarily what we're going to be looking at. We're going to take a look at something that you may have seen, maybe in a pre-calculus or an Algebra 2 class or a college algebra class, where we are going to take a look at the binomial series again. And see if there's anything else here that you may want to take a look at. This is just general information from what the College Board asks us to provide, saying this is what all of the material that this topic may touch upon. So, in the last section, meaning that this is going to be my lesson 10.5 in the curriculum that I'm using. So the last one, you just need to go back and find my 10.4 video if you need it. We created power series for functions using geometric series, substitution, long division, and term-by-term differentiation or integration. And we're going to see that again in this lesson as well. So develop a procedure in general for writing the power series of a given function that will have derivatives of all orders. We will find that every convergence power series essentially is going to take on the form of a Taylor polynomial. And that is essentially what and of course, Taylor polynomial, Maclaurin polynomial, same thing, just one, Maclaurin is centered at 0, Taylor is centered wherever it wants to be. Be sure you understand this theorem says if a power series converges to f of x, the series must be a Taylor series. However, the opposite is not true. It does not say that every series formed with Taylor coefficients will converge to the given function. And if you need it again, here is the definition of the Taylor polynomial. And here is our first example, asking us to find a Maclaurin series, in this case, of f of x, and give the first 4 non-zero terms and the general term. Now, this is going to be similar to things that we have done on other types of problems related to this information with convergence tests, divergence tests. We want to be able to take the function that was given to us, and we want to be able to compare it to something that is known, something that is simple to either remember or understand. Now, when it came to Maclaurin series, there were 3 Maclaurin series in previous lessons that you were expected to memorize. You were expected to remember something for sine of x, something for cosine of x, and what's going to help us out on this problem is we were expected to remember something for e to the x. Those were 3 transcendental functions that we need to be able to memorize to help us work these types of problems out. So this is where we're going to go with it, okay? We know, and let's go ahead and call that g of x, I guess. So we know that g of x is equal to e to the power of x. That's the given one that we are expected to remember, which as a series from 0 to infinity is x to the power of n over n factorial, which if we expand it out is 1 plus x plus x squared over 2 factorial plus x cubed over 3 factorial plus, and it keeps going. Now, the reason I'm going to stop at the third degree of the expansion is because we're asked to find the first four non-zero terms. So that will give us the first four non-zero terms. Well, now let's take a look at what was given to us and how we can utilize the known information to help us write the Maclaurin series for this function f of x. So we're given f of x to be equal to e to the negative 2x power. And what we're going to do is we're going to employ some substitution. In this case, I have negative 2x as a power, and that is what I'm going to use to substitute into the simpler known expression. So my series will now look like this, n equals 0 to infinity of, in parentheses, negative 2x to the power of n over n factorial. Now in the numerator, essentially we have three things. We have a negative 1 multiplied by a 2 multiplied by an x, and all of it raised to the power of n. So we can expand this out a little bit, and I'm going to say that we're going to have negative 1 to the power of n times 2 to the power of n times x to the power of n, all divided by n factorial. So here, when it asks you to find the Maclaurin series, there it is. There's the Maclaurin series. Now, finding the first non-zero terms, the first four non-zero terms would just be, let's take what we have here, and again, we'll do some substitution. Anywhere I have an x, I'm going to substitute my negative 2x. So this is going to wind up being 1 plus negative 2x plus negative 2x raised to the power of 2 over 2 factorial plus negative 2x raised to the third power over 3 factorial. So that could very well be construed as, okay, what are the first four non-zero terms? Those would probably work for the first four non-zero terms. You may want to think about simplifying them a little bit, especially if we want the general terms. The other thing that we can think about is we can say 1, so let's simplify this. That'll become minus 2x, and negative 2x squared will be a positive 4x squared over 2 factorial. And then the next one will wind up being minus 8x cubed over 3 factorial. And if you want to, what I would probably think of as the general term would probably be something simplified. I might look at these two here as, like, say, the first four non-zero terms. But the general term would be what this would be simplified. So this will be 1 minus 2x. 2 factorial is just 2, so 4 divided by 2 will give me plus 2x squared. And 3 factorial is 6, so 8 over 6 would simplify to be a negative 4x cubed over 3. And I would probably look at this one here as, the general term or the simplified value of that. So that's how we're using, again, I'm not sure if it's so much of a shortcut, but it's still a similar strategy to things that we were doing with some of our convergence tests. We're taking something that we know, something that we can compare it with to help us create, in this case, a new Maclaurin series. Now, the next part of this question, the follow-up here, it says use your answer to find a Maclaurin series for the derivative of f of x. Okay? So we can do that. It's not really going to be too challenging here. Let me pick another color. And in this case, we're going to look for the derivative of the expression that we had. So when I'm looking at the derivative, what I want to take the derivative of is really, I'm looking at this expression here for something I'm going to take the derivative of. So right now we have f of x to be 1 minus 2x, and then we had plus 4x squared over 2 factorial plus, nope, minus alternating 8x cubed over 3 factorial. So now if I want to find the derivative here, we can do that. F prime of x, in this case, will give me a 0 here, minus a 2 here, plus 8x over 2 factorial here, and then minus 24x squared over 3 factorial. And now we can simplify this a little bit more. Of course, the 0 doesn't matter, so we have negative 2. 8 over 2 factorial simplifies to just be a 4, so plus 4x. And negative 24 divided by 6 will wind up being minus 24 divided by 6 is 4x squared. Okay, so that would be the derivative of the Maclaurin polynomial, but we're looking for a series. Okay, so what I'm looking at to help me be able to identify the series, and let me pick another color here. What I'm looking at to be able to identify the series now is really this expression. Okay, how can I take that? Because what we're going to do is we're going to just say plus dot 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 dot. We're going to be able to write a new series for this. So here we're going to start it off n equals 0 to infinity. And we can see we're still alternating. So we have to have our negative 1 raised to the power of n. Looking at the term numbers themselves, here when n is equal to 0, when n is equal to 1, when n is equal to 2, when n is equal to 3, and so on, we can see that the x values are always going to be 1 minus n as far as the exponents on the x's, and the expression itself, I'm looking at getting, let's see, everything's going to be in terms of a power, and it's going to be whatever the power is. Let me take another look at this. I'm not seeing something here that I saw before. Give me one quick second. Okay, yeah, there's something I was meant to, I don't know, I was just looking at it and I was having a hard time saying, well, how do I make the n value become, when n is 1, how does it become the 2 and the 8 and the 24 and so forth? Well, what I'm going to do is I'm going to take the 2, ooh, I can turn my pen back on. I'm going to take the 2 and I'm going to raise it to the power of n. Well, now if you look at that by itself, 2 to the power of n doesn't give me the numbers that I have in that polynomial expansion. But if I take that and I multiply it by the n value itself, it does work. Now the x terms are going to be x to the power of n minus 1, and all of it is going to be over n factorial. So this is the Maclaurin series. Now, before we move away from this, I would just like to point out, let's go back to here. Let's just go back to here real quick. What if I took the derivative of that? Could I take the derivative of that series? Negative 1 to the power of n times 2 to the power of n times x to the power of n over n factorial. If I take the derivative of that, we're going to wind up right back there. we're going to wind up right back there. So we could have taken the derivative of the series itself, piece by piece, which is one of the skills that we're expected to be able to look at in this particular skill set, the topics that we're talking about here. And hopefully, we're able to connect some dots and create some good understanding. Okay. So for this next one here, this one is going to, again, it's in the form of that rational expression. It says, evaluate the indefinite integral as a power series and find the radius of convergence. Well, just like what we've done with a lot of other things, with our sequences and series, we're going to be able to look at this as something simpler than what we started off with. The first thing that I'm going to do for a problem like this is, in this case, I'm going to factor the t out of the numerator. Okay? And the reason why I want to factor the t out of the numerator is what I know, something that's about as simple as it gets. If I look at this as 1 minus x, if I look at that as a power series, that is just x to the power of n. So we're going to be able to look at this as some known quantity, and remember, we're looking at essentially this in the terms of 1 over 1 minus r. Okay, so the first term a is with the 1, and the constant ratio is whatever this is. So in this case, the constant ratio is just the x. We don't pay attention to the negative sign, we just pay attention to the value. So that's how I'm getting, okay, with this is a very simple power series that we're able to create here. Now, and so that's kind of what I'm doing. That's why I'm going to factor the t out of the numerator, is because I would like to have that top part to match this thing here. We want it to be a little bit more simple, so I'm going to factor out the t in the numerator and see what we end up with. So when I factor the t out of the numerator, I'm going to just say t times 1 over 1 minus t cubed dt. Okay? And just like what we've done before, we're going to now substitute the t cubed we're going to substitute the t cubed in for x of the known power series. Okay? And so here we're going to look at t as a constant. So I'm going to say t times the power series from n to 0 to infinity. We're going to just substitute the t in for x cubed, or for x to the n power. So that becomes t cubed to the power of n. And here, I guess I really don't need, I probably should have just left that t here, because they do have a common base. So t to the first power times t to the 3n power, that will be t to the 3n plus 1 power. And now this is going to give us the indefinite integral of t over 1 minus t cubed dt to be equal to the indefinite integral of that series. Three n plus 1. I didn't write that very nicely. T to the 3n plus 1 power. And we can integrate that piece by piece. I mean, there's only one piece there, but we use our general power rule again to kind of perform our integration. Now in this case, we are going to have a constant. I'm going to put my constant first. And in this case, we're taking the integration of t raised to the power of 3n plus 1. So we add 1 to that, and that's going to give me t to the 3n plus 2 power. And it's all going to be divided by the reciprocal of that, which would just, or multiplied by the reciprocal of that, which would just be the same thing as dividing by 3n plus 2. And so here, this is what I would look at as the power series. Now, we don't know what C is necessarily, but in this case, if you say, what are we looking at? If T is equal to 0, we would wind up with 0 equals 0 on both sides. So in this case, C is going to equal 0. But the last thing that it was asking us to do, which I'm not sure if you guys are all seeing it or not, but it is asking us to find the radius of convergence. Okay, so we do need to do one more step here. We need to find the radius of convergence, so that'll be the fourth thing that I do. The radius of convergence, of course, is going to be looked at with the ratio test, which if you don't remember the ratio test, it's the limit as n approaches infinity of a sub n plus 1 over a sub n. So in this case, I'm going to look at the limit as n approaches infinity of the absolute value. In this case, we're going to look at this guy here. This is what we're looking at to do our ratio test. So if I say n plus 1 on this one, I'm going to wind up with t 3n plus 2 plus 1 will give me to the 3n plus 3 power over 3n plus 3 again. And I'm going to multiply it by the reciprocal of that rather than dividing with it. And that'll give me 3n plus 2 over 3, nope, t to the 3n plus 2 power. And we're going to wind up simplifying. So n approaches infinity. The 3n plus 2 over the 3n plus 3, those aren't really going to simplify, but I can take the t powers, the t raised to the 3n plus 3 power, and subtract the exponent of the t raised to the 3n plus 2 power. So if I say 3n plus 3 minus 3n plus 2, the 3n's are going to cancel out, and 3 minus 2 is going to give me just t to the first power multiplied by 3n plus 2 over 3n plus 3. Now, as n goes towards infinity, this part here is just going to simplify, not 0. It's going to simplify to be a 1. So the limit in this case is going to be the absolute value of t. Now what we know about the geometric series is that the constant ratio, t in this case, must be less than 1. And if we were going to solve this, in this case, this will wind up being the radius. It's a Maclaurin series, so it's centered at 0. I know it's centered at 0 because we're not adding or subtracting anything to the t value itself. So here, we're going to be centered at 0. We're going to go to a positive 1, and we're going to go to a negative 1, negative 1. So the radius of convergence in this case is a 1. Okay. Okay, so this example asked us to do kind of piece by piece integration, or I'm sorry, differentiation in order to I arrive at what the uh, radius of convergence would be and what the new series would be. So now what we're going to be taking a look at in this case, let's see, am I on the right page? Taylor series and differentiation. Nope, I am not. There we are. Now I'm on the right page. Sorry for the confusion. When differentiating a Taylor series, just take the derivative term by term. And so I guess I was just thinking ahead. This is where we were going. Now, what they're asking us to do here, let's see. I'm not super keen on this example right here. I'm not entirely sure what they were asking us to do with it. I know how I'm going to approach the problem when we are given a specific task in mind, but when differentiating a Taylor series, take the derivative term by term. The radius of convergence of the derivative will be the same as the original series, but the interval of convergence could change. So that's why it says check your endpoints. Okay. Now, for this one here, if I were going to find the derivative of this, we could express this as a series. Obviously, we've done that a few times. This one would just be 0 to infinity. This one would just be x to the power of n, and we could write out the first several terms of the actual series itself. But find the derivative f prime of x. Well, here this is literally just asking us to find the derivative. Oh, sorry for the bell. And we're going to say 1 over 1 minus x squared, or quantity squared, like that is the derivative. So we are going to be using differentiation to help us with some of these problems, but it's not necessarily, again, I'm not quite connecting what the example here was supposed to be for those of you that are following along with the notes in class. But this example gives us a clear objective. Differentiate to find a power series representation and the radius of convergence. Okay. Now, the idea is always to think about if we're talking about a power series, the idea always is in some way we're going to be talking about this expression 1 over 1 minus r. Because that is the basic formula that we use for the sum of a geometric series. And that's essentially what we're talking about here. The power series, we want it to look like this in some way. And the way that I'm going to take my approach to this problem, 1 over 1 plus x quantity squared, it's not the same thing as that last example was. What it's asking us to do now is to create a power series in that fashion. Now, the way that I'm going to do this is I'm going to compare it with something that is going to be a little bit more straightforward. I'm going to compare it with the expression 1 over 1 plus x, something that's going to be a little bit more straightforward. And now what it's going to ask us to do, okay, well, we're going to use that trick that we've done in the past where, this part here needs to kind of match this part here where we need to actually have it in the form of 1 minus r. So we need to have that double negative thing there. So I'm going to say this will be the same thing as 1 minus negative x. And so that would tell me that a, in this case, is the 1 on the top, and the constant ratio in this case is going to be negative x. And that will allow me to write a series that says this is the same thing as the series of, we're going to have a negative here, so negative x to the power of n, which would just be negative 1 to the power of n times x to the power of n. That's not a very nice n. There we go. Well, now that I have that series, now this is where I can wind up taking the derivative of something. Okay, so that's what I'm going to do now. At this point here, this is where I take a derivative. Okay. Now, if I take the derivative of the expression as it was given to me, if I take the derivative of 1 over, or not the derivative as it was given to me, if I take it with the one that I'm comparing it with, 1 plus x, that derivative is going to be negative 1 over 1 plus x quantity squared. Well, I'm going to do the same thing with my expression. I'm going to take the derivative of my series, I should say, not my expression. The derivative of my series, negative 1 to the n power times x to the power of n. And when I take the derivative of that, I'm going to get my series n equals 1, nope, not 1, 0 to infinity of negative 1 to the power of n times x to the n minus 1 power. Okay, so when it's asking us to do, it says differentiate to find a power series representation of what we were given. This is what I'm looking at. That's going to be the power series representation of the expression as it was given to us. Now, the next thing we're asked to do is find the radius of convergence. So the last thing that we're going to look at here for the radius of convergence is this is where we need to do our ratio test. And if I take the ratio test of the expression that we have, in this case, we're going to say the limit as n approaches infinity of the absolute value of a sub n plus 1, in this case will give me negative 1 to the n plus 1 power times n plus 1 times, and I don't really need a parenthesis here, times x to the n plus 1 power. And we're going to divide it by, and in this case I'm going to divide it because I'm not dividing by a fraction, so I'm not going to multiply by the reciprocal. In this case, negative 1 to the power of n times x to the n power. And we can simplify that, obviously. Limit n approaches infinity. The exponents, when we subtract them on the negative 1, is just going to wind up with a negative 1 itself, so negative 1 in the top. The n plus 1 over n, those don't really simplify to each other, so I'm going to say n plus 1 here. And the x terms, again, subtract the exponents from each other, and n plus 1 minus n is just going to give me x to the first power, and all of it is going to be over n. Now, this part right here, the absolute value of the negative 1, we can ignore that because, not ignore that because the absolute value of negative 1 is just 1, so it really doesn't have an effect on anything. As n goes towards infinity, n plus 1 over n is going to simplify to be a 1, so I'm left with just the absolute value of x for my limit. And again, based off of the idea that the constant ratio, which that's what the x is representing, it's representing the constant ratio of a geometric series, the absolute value of x needs to be less than 1. So in this case, the radius is going to be 1, because if we were to, again, kind of set up and solve the compound inequality, Here we're going to wind up with x to be less than 1 but greater than negative 1. And because we're not adding or subtracting anything directly to the x itself, this one is going to be centered at 0. And the radius of convergence in this case is just going to be a 1. And there's how we're going to be taking the derivative of the expressions to help us create a power series representation. And this one is going to go the opposite route, and what it's telling us here, we can also integrate Taylor series term by term, given that integration is the inverse operation of differentiation. Now, this one here, again, is going to require a little bit of problem solving skills, a little bit of, okay, well, what do we know about what was given to us? And even though it's telling us we're going to use integration because it's it's the inverse of differentiation, we can't completely ignore the derivative concepts that we're going to see in this problem either. Okay, so just like a lot of things in math, what do we know with the information that was given to us? What can we do with it? And then at that point, do I need to maybe try integration or some kind of differentiation? So find a power series for the function f of x is equal to the inverse tangent of 2x using substitution and integration. Now here again, this is why I'm saying that you can't just keep the blinders on and say, okay, well it said to use integration, so how am I going to integrate this? Well, let's think about what we know about inverse tan or arctan of 2x. I know that the derivative of arctan of x is u prime over 1 plus u squared. Therefore, according to what we know about the expression that was given to us, the derivative of tan inverse of 2x, where u in this case would be the 2x, I can recognize that u prime, the derivative of u, will be 2, and u squared will be a 4x squared. Okay? Now, the reason why I want it written like that, I want something in a form like this, is because what are we doing? We're creating a power series, which the power series means that we want something in this form. That's why I'm recognizing that I want to do a derivative of the inverse tangent, so that way I have something that resembles the power series itself. And now we can use our tricks here to recognize what we're going to wind up getting. Now in this case, the general power series, we're going to say n is equal to 0 to infinity. Remember, that's just the first term times the constant ratio raised to the power of whatever. Okay? So what are the a terms, and what's the a term and the r term going to be from what we have been given? And let's see, get a slightly different color here. What are the a terms and the r terms going to be to plug it into something that looks like this? Okay, well, what I'm going to do is I'm going to say 2 over, and again, we have that negative sign that we need. So I'm going to change that plus sign into a negative sign with a double negative. So I'm going to say 1 minus, in parentheses, negative 4x squared, close parentheses. And so now I can see that a, in this case, is 2, the value at the top, because, again, we can think of a as being that. And the first term is going to be, or the constant ratio in this case is going to be the negative 4x squared. So now that I have that, we're going to take both of these and substitute them in here and see what we end up getting. Well, now that I've done that, my geometric representation, or my power series, in this case, is going to be the summation from n equals 0 to infinity of 2 times negative 4x squared to the power of n. Now we want to clean that up a little bit. We want to expand it and make sure that we understand exactly what's going on here. So 0 to infinity. And if you want to, you can think of just pulling the constant of 2 out if you really want to. And I think, I don't know, do I want to pull the 2 out? I don't think it's really going to make that much of a difference. But I don't know, we'll go ahead and just pull the 2 out as a constant, and then we'll just kind of expand all of this stuff that we see here. So I definitely have a negative 1 raised to the power of n. I have a 4 raised to the power of n, and I have an x squared raised to the power of n. And that would be essentially a geometric power series, or that would be your power series of inverse tan of 2x. Okay, so let's just go ahead and put that here. So tan inverse of 2x is equal to that. Now that I know that, this is where we can actually do the integration. Okay, and here with the integration, and something's clicking over here. Give me just a second. Okay, sorry about that. I'm not sure if it was coming up on through the microphone there, but something was making noise on my side here. So now, getting back on track here, what we're going to do now, this is, once I have this geometric representation, now I have my power series. This is where we're going to actually do the integration of the expression that we have. So let's go ahead and do that. And let's see. Let's try this orangey looking color here. So here, this is where we're going to do our integration, and I have that 2 that I pulled out as a constant just so I could show you, really what we're going to do, and I'll just leave it out for the time being. Obviously, it's going to have to go back in to the expression that we have, n equals 0 to infinity, because one of the things that, and this may be actually one of the things that the students are going to trip up on, is that here, the 4 is the same thing as 2 squared. And the reason why I want that is because I recognize that I have, if I rewrite that as a common base, I can simplify the 2 when I bring it back in. So this will be 2 squared to the power of n. And if I use the power rule here for the exponents, that's going to give me x to the 2n power. So now I'm going to reintegrate the 2 constant on the outside of the summation. And this has an exponent value of 1, so the 2n plus 1 is going to give me, and I don't really need parentheses when I do this at that point, 2 to the 2, and I started to write n. Let me just clean it up. To the 2n plus 1 power, 2n plus 1 power, times the x to the 2n power. Now we can actually do the integration. Find the antiderivative of the expression that we have here, and we're going to say that the inverse tangent of 2x will be equal to a constant when we do the integration, because we're doing indefinite integration, plus the summation of, we're going to have negative 1 to the power of n, and the next part here is going to be, what am I doing here? Hold on a second. I had to take a break here, and give me 1 second. I'm not seeing something. I want to make sure I write it down right. Okay, sorry. I am recognizing that I made a mistake, and I'm too far into this video to want to try and start over because I don't really have much in the way of editing properties. So I'm going to come back to here, essentially where I started writing in this orange color, and we're going to take all of this stuff here, and we're going to remove it because I made a mistake the way that I wrote my constant when I pulled it out. I didn't put it in the right spot. Okay, so restarting at that point. All right, so we have inverse tangent of 2x to be equal to, this is where we're going to do the integration. So the 2 is where I had it in the wrong spot, and that was throwing me off when I tried to do my integration. We're going to do here n equals 0 to infinity, and again, I'm going to just rewrite this negative 1 to the power of n. The 4 I'm going to rewrite as 2 squared to the power of n. Now we're still going to wind up bringing that 2 back in. But here, all right, hold on. I'm still confusing myself. Sorry. Okay. Back to the problem. X to the 2n, and I really don't need the parentheses on that one, but here we're going to start taking the integration. So here I'm going to have 2, and we just are going to have our summation here. N equals 0 to infinity, and the negative 1 integration stays negative 1 to the n power. Same thing with this one here. I'll just write it as 2 to the 2n power. And this one, the x, that is going to become x to the 2n plus 1 power. And that is going to become the multiplied by the reciprocal of that expression on the x, and I get just 2 to the n plus 1 power in the bottom. Now this is where I bring the 2 back in, because if I bring this 2 back in, into the expression here, then that is going to be what gives me exponents that match throughout the entire problem. So let me do that now. So I have my summation n equals 0 to infinity. And at this point here, I'm going to go ahead and put my constant into the problem because I didn't write my constant here. I'll go ahead and put it. And that'll give me negative 1 to the power of n for my alternating expression. And then we're going to have times 2 to the 2n plus 1 power times x to the 2n plus 1 power, all of it divided by 2n plus 1. And that is going to be my final expression. The only thing that we want to check is what is the value of c going to be. So we can check this when x is equal to 0. So if I have x is equal to 0, Let's get a color here that we can substitute. If x is equal to 0, then this whole thing goes to 0. And if I have tan inverse of 0, that also equals 0. So I wind up with 0 equals c plus 0, so that means c is equal to 0. So c is equal to 0 in this case. So my final expression is really going to be what we had, but without c. So I'm going to just say my final expression, tan inverse of 2x, is really just equal to the summation of n equals 0 to infinity of -1 to the power of n times 2 to the 2n plus 1 power times x to the 2n plus 1 power, all of it divided by 2n plus 1. And that is my final solution here. So sorry I flubbed where I put the 2 on that one. But again, think about what we know, okay? We know we need it in some way to look like this expression here. You know, we need it to look something like that. That's why I wind up taking the derivative of the expression as it was given to me, so I have something with which to work. Then I have the ability to put it in a series, and then I can integrate the series, and when I'm done integrating the series, check to see what the value of c is on this one. It's not asking us to find any kind of interval or radius or anything on that one, so we're going to just, at this point here, say we're done. Now this next bit here, this is where we're getting into into a binomial series. Now binomial series hasn't really popped itself up in calculus so much so far. It is something that you may have seen in pre-cal, college algebra, something like that, when you're talking about permutations, combinations, things like that. For instance, this bit here, I don't know what color I'm looking at. This bit here, the stuff in these kind of exaggerated parentheses, usually they're indicating a combination. Usually they're indicating you're dealing with a combination, and we read it, but usually it's written like this, where it's kind of upside down from what we're given for the binomial series here, and we read it as n choose k, and usually what we look at it as, where we say like n like this to indicate that we're doing a combination, and we have n factorial divided by k factorial times n minus k factorial. That's usually what we think of, or at least that's usually what I think of whenever we see factorial stuff. I'm sorry, not factorial, but the combination, when we're talking about combinatorics, permutations, combinations, things like that. Now, the way that they're looking at it here, notice what they're specifically giving to you here to recognize that we're doing a binomial series. The last series we want to develop is a function in the form of this. This is specifically what we're looking for, is a binomial series. Essentially, you know, we have the two terms, 1 plus x raised to some power. This is where we're going to start getting into we could start getting into Pascal's triangle to try and help us predict what the numbers are going to be as the value of k in this case gets really big. And and if you notice the way the binomial expansion is being done here, it's similar to what the combination typically would look like. But of course, we're multiplying the k choose n in our case. We're multiplying it by x to the power of n. And you can kind of see that what's going to be going on up here. Oops, I didn't mean to have my highlighter here. What's going on here? I still have my highlighter on. It's been a day. Let me just tell you that it's just been a day. So they kind of look the same. Okay, not exactly, but they kind of look the same. And so this is, I'm just giving you this here for reference because if you've taken pre-cal or if you've taken college algebra or if you've seen this in another course, that's what it is referring to is a combination where we read it as n choose k. But in this case, we'll go ahead and stick with what our calculus information is giving us for a binomial series where we're going to say, in this case, k being our exponent value, and n is, of course, however many terms that they're going to go through. So we would look at this as the series of k choose n multiplied by x to the n power will be the expansion of the expression that we see in our notes. We're not going to try and overcomplicate it. I'm just trying to make sure that everybody understands that you may have seen something similar to this talking about combinations. Now, find the Maclaurin series, so it's a Taylor series centered at 0, for the expression of 1 over x plus, or 1 plus x to the power of 4. Now, if you notice, it doesn't really fit the expression for what we have here. If you notice the expression here and the expression here, we have something that's rational versus here we have something to just a binomial raised to a power. But we can easily change the denominator to be 1 plus x to the power of negative 4. And if we do that, then we can use the binomial series to help us out. Now it says find the Maclaurin series in this case, and here I don't know if we're going to really write it as a series as opposed to just writing it out. Let me just double check real quick if I want to continue, if I want to write this out as a series, or if I just want to write it out as a because this is what it's asking us to do. It's asking us to kind of expand it out and to do something like that. But when they say series, I'm usually thinking, okay, well, we want something that looks like this. What's that going to be? Okay. But I think in this case, we'll just stick with this here. Okay. If we need to actually write a series, we could do that. But let's just kind of stick with the binomial expansion as we see it given to us. So here, and again, I'm just kind of putting this here in case anybody needs to see it, so you don't have to rewind or flip back or anything like that. So based off the expression that we have, and let me go to another color here. Based off of the expression that we have, where it says 1 plus x to the k power, in this case I'm going to get 1 plus x to the negative 4th power. And it's going to be equal to this series like that. And so I guess we're like I said, we're going to be looking at the expanded series of, in this case, k is negative 4, and to the and n is just n, the number of terms that we're going to be looking at. And here we're multiplying it by x to the power of n. So when we expand this according to the binomial series expansion that was provided for us, we're going to start off with 1, and then we're going to say plus k, which in this case is negative 4, times x plus k, again, negative 4, times negative 4 minus 1 over 2 factorial. And I'm forgetting my x squared here. And then we'll say again, plus, and it's not telling us how far to go. So I guess I think I'll just make this my last one because it's not really telling us how many terms that it's asking for. So again, we'll say -4 times, we'll keep that in parentheses, -4 times -4 minus 1 times -4 minus 2 over 3 factorial, and I forgot my x cubed here. And that's all we're doing based on the binomial expansion. Of course, if it kept going, we would wind up with k minus 1 times k minus 2 times k minus 3 times x to the 4th power over 4 factorial. But we'll go ahead and stop here and see what we end up with. Now I'm going to simplify. Here, this is -5. Here, of course, again, that's -5 again. And here, this will be -6. The 2 factorial is just 2. The 3 factorial is 6. So I'm going to wind up with something that says 1 minus 4x. So in the top here, -4, -5, -20 over 2 will be a -10x squared. And here, this and this will just simplify to be -1. So that'll be -20 times -1. It'll be -20x cubed. And it would keep going, but that's what we're looking at there for our expanded binomial series. And that's all the examples that we have for the binomial series. So maybe it's not going to play a huge role for things on your AP test. Now, I just love it when our notes give us an entire page to do one problem. It just makes me feel all warm and tingly inside and says, we have a lot of stuff that we're going to have to write down here. So this last example, they're giving us a definite integral from 0 to 1 of x cosine x cubed of dx, and it wants us to approximate that definite integral to within 3 decimal places. So, okay. Just like a lot of things that we've been doing, I want to think about this and I say, okay, can I compare this to something that I know already, something that's going to be a little more simple, and then I can build up from there with, doing some substitution. And I do know that this one is going to be a Maclaurin, or it's going to be centered at 0 because we're not adding or subtracting anything to x. So this one is going to be centered at 0. And I do have a Maclaurin series for cosine that I can refer to. And that's how I'm going to start looking at this. Recall, in this case, the cosine of x for a Maclaurin series is going to be equal to n equals 0 to infinity of, and it's alternating, -1 to the power of n times x to the 2n power, and all of it is divided by 2 times n factorial. Okay, so now that I know that, now I can start substituting a little bit. Here in this case, and it's not real clear, the cosine itself is not cubed, it's x cubed inside of parentheses. That's how it really should be written. So here in this case, cosine of x cubed, we can do some substitution here and wind up with our series n equals 0 to infinity of -1 to the power of n, and wherever I have an x, I'm going to substitute the x cubed now. So I'm going to wind up with x cubed raised to the 2n power over 2n factorial. And of course, we can simplify that a little bit with the exponents on the x, and I'll have -1 to the n power times x to the 6n power over 2n factorial. Okay, so now I can bring in the x that we haven't done anything with. Uh, so that means if I bring in the x times the cosine of x cubed, this will result in me getting, here we're just kind of incorporating a constant of x. We're saying x multiplied by that. So I'm going to wind up with my series n equals 0 to infinity. And I'm going to wind up with negative 1 to the n power. We're bringing in the x, which of course is multiplied by x to the 6n that was already there. And all of it is divided by 2 times n factorial. And of course we can simplify the expressions here. So my final n equals 0 to infinity is going to be negative 1 to the power of n times x to the 6n plus 1 power divided by 2n factorial. That is where I'm starting based on what I already know. Now remember, if you don't know this stuff here, you're sunk. You don't really have a starting point with which to work on, because sine, cosine, and e to the x were all Maclaurin series that you will be expected to have memorized. And that's where I'm getting that information from, to start off with something simple and going through and adding the information by doing substitution with something that I had already knew, or that I'd already known. Okay. Now this is where we can start doing some integration. Okay. So the second thing now is we're ready to integrate. So I have my definite integral from 0 to 1 of x times cosine of x cubed to, or multiplied by dx. And that is going to be equal to the integration from 0 to 1 of the power series that we just created, n equals 0 to infinity of negative 1 to the power of n times x to the 6n plus 1 power divided by 2n factorial. Okay, so take the antiderivative of what we have, and I'm going to wind up with my series n equals 0 to infinity of negative 1 to the power of n, and adding 1 to the exponent value of the x is going to give me 6n plus 2 over, and we still have the 2n factorial in the bottom, but we also have to divide or multiply by the reciprocal of the exponent on the x, which would just be the same thing as dividing by 6n plus 2. And we're evaluating it from 0 to 1. And I'm needing to move down some here. So now we can start doing our substitution. All right, and I'm going to have n equals 0, infinity. So anywhere I have an x, I'm going to put my 1. So this is negative 1 to the power of n times 1 to the 6n plus 2 power over 6n plus 2 times 2n factorial. And we're going to subtract n equals 0, infinity, negative 1, n. Now we're going to substitute 0 to the 6n plus 2 power over 6n plus 2 2n factorial. And here because of the 0, we're multiplying by 0, and we're going to say, 0 divided by something. This whole thing is going to simplify to be 0. This whole thing is just going to simplify to be 1, and that will leave me here n equals 0 to infinity. It'll basically just leave me the -1 to the n power over 6n plus 2 times 2n factorial, like that. Okay, so there is my integration. Now, what we're being asked to do is to approximate this to 3 decimals. Okay, so we're almost there. Now that we started off with something simple, so that way we could actually get the series that I have underlined in kind of that pinkish color. We had to be able to get that based off of our prior knowledge with our Maclaurin series for cosine. And then we were able to do our substitution, got our series, and now we could do our integration. So we've done our integration with the definite integral that we were given from 0 to 1, and we're left with the series here that I have underlined in black. Now it's time to try and approximate the expression to 3 decimal places. So here, let's go ahead and go back to this green color. And I'm going to pause the video so I can write some stuff down here. Okay, so by the alternating series estimation theorem, the estimate that we're trying to get is at most the absolute value of the first unused term. So what we need to be able to do is we have to take the series and we have to expand it so that way we can figure out where do we want to stop and at what will be the first unused term that we're probably going to use as our reference. So I'm going to take the expression that we have, n equals 0 to infinity, of -1 to the n power over 6n plus 2 times 2n factorial, and we're going to start expanding it. Okay, so here, let's say, when n is equal to 0, I'm going to wind up getting uh, -1 to the 0 over 6 times 0 plus 2 times 2 times 0 factorial. And we'll just keep doing that for a few terms. So I'm going to go ahead and pause the video and write those out again. Okay, so this is all the space I had was to be able to write the first 4 terms. So, this is when you don't necessarily need to put this here, but n equals 1, n equals 2, n equals 3, and so on. Now we're going to simplify each of those, and when I do, -1 to the 0 power is just going to be 1. 6 times 0 plus 2, and 2 factorial is just going to be, or 2 times 0 is 0 factorial. 0 factorial is actually 1, so I wind up with a 2 in the bottom. And here, -1 to the first power will give me a minus sign, and 6 times 1, 6 plus 2, 8 times 2 factorial will give me, let's just write 8 times 2 factorial. And then we're going to wind up with a plus, and then I'm going to wind up with 14 times 4 factorial minus 1 over, so here 1820 times 6 factorial, which of course will be just the 1/2 minus 2 factorial is 2, so that's 1/16 plus, and here I'm not going to try and do the mental math here of multiplying 4 factorial by 14. This is where I am getting my calculator out, and I'm going to work with the calculator here. So 14 times 4 factorial is 336, and then we have minus 1 over, and definitely 20 times 6 factorial, I'm not going to try and do it in my head. That worked out to be 14,400, okay? So we're trying to be accurate to within 3 decimal places. So let's just, if we're trying to look at something as the first unused term, well, let's look at this one here. Let's just presume that this will be our first unused term and see, well, what is the value here? Well, if I take the absolute value of the negative 1 over 14,400, we're going to get, on my calculator, I'm getting 0.00007. So because I have these 4 decimal values, as long as I have something that doesn't, if the sum of these 3, as long as they kind of give me something in this area, then I can say, because the next one, the first unused term has 4 unused zeros, or 4 zeros for, after the decimal point, then we can say that, we will definitely be within a margin of error that's acceptable, for 3 decimal places. So here, again, I'm going to go to my calculator and I'm going to find the sum of those first 3 fractions. And it didn't even give me a nice fraction to work with. It gave me a decimal, and I'm going to say the decimal is 0.440. Okay? And so because the next unused term has 4 zeros, and here I'm only looking at it to 3 decimal places, I can say that this estimate is correct to 4 decimals. And that is going to wrap up what we're looking at here in this example. Again, it's a process. To be sure, it's a process. Is it doable? Yeah. Is it going to take a little bit of work? Yeah. And you definitely, if you don't remember what your Maclaurin series is for cosine, if you had this on a test, you're going to be sunk. You got to have that memorized. Because without that, we don't know how to do our substitution to get to our series that we're going to look at here for x times cosine of x cubed. And without that, we can't do the integration. And without that, we can't get the first several terms to get the sum to 3 decimal places, or figure out what the first unused term value would be. And that is going to wrap up what we're looking at for this lesson in Taylor and Maclaurin series, where again, it's not something that we're using to do an estimation with, but instead it's showing us that if we have a converging p-series, we will be able to create a Taylor or Maclaurin polynomial from it. And in some cases, we'll have to be able to do differentiation and integration, and for each piece. And of course, we can't forget our binomial series, which made a brief but not quite insignificant appearance. But we're going to wrap it up here, guys. Thanks for watching. I hope you learned something, and we will. My computer is freezing, so hopefully the recording is still going. Stop. Let me stop the video. It's just been one of those days, guys. What can I say? If I touch it up here, nope. Well, anyway, go ahead and stop watching the video. We're done. I'll try and figure out why it's not letting me actually stop the video now.